Right, we're going to move on a little bit, but before we do, I want to show you a real 5.2 valve. So there's the real 5.2 valve there, that's what they look like. Remember, a 5.2 valve is so called because it's got 5 ports and 2 states. And when you look at this thing, you go, right, well, I can clearly see 5 ports on it. 1, 2, 3, 4, 5, right? This is a pilot 5.2 valve, by far the most common 5.2 that you guys will use or see in engineering science. So that means that 2 of these connections, 2 of these ports on the body of this, they must be for the pilot connection. And it's these 2. What's nice about the 5.2 valve is it physically laid out almost identically to the symbol that we draw, a horizontal rectangle with the actuators on either side. So these ports are actually for the pilot air. This is our input port that we would connect to the manifold, to main air, and then these are the 2 output ports that connect to the cylinder. So of the 5 physical ports that are on this, only 3 of them appear in the name 5.2 valve. Where's the other 2? So the other 2 are the exhaust ports. So the other 2 are there. They're on the underside. They just don't have any ports screwed into them. We don't have to. All they're doing is exhausting air from the dead side of a cylinder back out to the atmosphere. So that's what a double acting cylinder looks like. You need to be careful because a pilot 3.2 valve looks exactly the same, right? So how can you tell the difference? The only way you can tell the difference is by looking at the symbol on them. I don't know if you can see the symbol because my lighting's pretty poor and everything's pretty backwards and upside down, but the symbol's on it. So you need to always know the symbol first of all and then look for the symbol. What we're going to go on in this presentation to look at is what's called speed control. So the idea is with a double acting cylinder in our compressors, our compressors run at 3 bar. So if we provide an outstroking signal, on that port, then the cylinder will go quite violently, quite fast. And that's fine for a lot of applications, but for a lot of applications it's not fine, and the reality is you would want the cylinder to go slowly. You would want to be able to control the speed of operation of the cylinder. We're going to talk about 2 things ultimately. We're going to talk about speed control and time delay, and everybody always mixes them up, right? Speed control is when the cylinder is in-stroking and out-stroking. As soon as you press the button, as soon as you actuate the 5.2 valve or whatever you do, the thing will move, but it will move slowly, not jerkily. I can't actually pull this out. This cylinder's pretty old, but it moves nice and slow. That's speed control. And the user will be able to adjust something to create speed control. Whereas when we get to time delay, the idea is that when you actuate the thing, nothing will happen until your value of time delay is fulfilled, at which point it will move at full pace. Yeah, time delay and speed control are 2 different things, so let's not mix up speed control and time delay. Everybody always does. So how do we achieve speed control? Speed control is all about reducing flow rate. Okay, everybody mixes it again. People mix things up. They mix up pressure and they mix up flow rate. We have devices that are called we have devices called flow restrictors. Okay, so a flow restrictor is the symbol for a flow restrictor is drawn like that. Okay, with an arrow across it because the user can adjust the level of flow restriction. So if the restrictor is all the way off and you provide a positive air signal here, ultimately this side will get to the same pressure. It will just take longer. And pressure is that function of if as you increase pressure on something that can move, at one point it will move, depending on how much resistance it's got to that pressure. And that's what's happening inside a 5.2 valve. So inside the actual 5.2 valve, there's a little plastic spool that moves left and right. If we provide an air signal here, we'll push the spool across, but it won't move until the pressure gets high enough to move it. And it's the same in the double acting cylinder. If we provide an air signal here, it's not going to move until the pressure gets high enough to move it, right? So if we reduce the flow rate, it'll take longer, as much as maybe this signal is coming from main air and is at 3 bar or 0.3 newtons per millimeter squared, right, pressure. We put it through a flow restrictor. This side will still get to 0.3 newtons per millimeter squared. The pressure will equalise, always equalise on on both sides of a component if the air can get through. And all we are doing is increasing the amount of time it takes to get to that massive pressure through a flow restrictor. So all the flow restrictor does is basically reduce the inside diameter of the channel through which the air can pass. So that's what's happening. I was going to write 3 bar in there, but we don't actually use 3 bar. Right? We shouldn't be using bar, we use 0.3 newtons per millimetre squared. So, flow restrictors, it's got an arrow on it because the user can adjust the amount of restriction. So you could run that restrictor all the way off so that it's almost like it's not there. Or you could tighten it right down so that it would take a very, very long time for this side to build the pressure up to equalise. Okie dokie. We don't use flow restrictors. We use something called, so that's a flow restrictor, right? We use something called restrictor. A unidirectional flow restrictor. What this means is it will only restrict flow in one direction. Uni meaning one, directional, direction. Flow restrictor. What does it look like? What's the symbol for it? So the symbol for it is, so it's got a flow restrictor in it, obviously. But then it's got a bypass around it, a one-way bypass. So the idea is that if air can bypass the restrictor, it will. Yeah. So what we do is we put a one-way gate in there, and you've seen this type of symbol before. Maybe a wee ball and cone. So if we increase the air pressure on this side, will the air pressure go through the restrictor or will it go through the bypass? So we've got the ball on this side. If we increase the air pressure, that ball will get blown into the cone and block the bypass route. So if this side's high, all air goes through the restrictor. Restricted. If, on the other hand, we make this side high pressure, then the ball will be blown out of the cone and open this channel. Air can get around the ball. So in this direction, it's full flow because no air will try to go through the restrictor when it can. You know, it's like there's a path of least resistance thing happening here. So this is a unidirectional flow restrictor. It uses a little ball and cone bypass on it. And what's really, really nice about the symbol is, see the cone in the bypass symbol part of it? It forms a wee arrow that points in the direction of restriction. So you know that if the symbol's facing this way, air going that way is getting restricted, and that will come in depending on how we use it. Okay, so that's a unidirectional flow restrictor. What does it look like in real life? So obviously you get different models of them. The ones we use are these wee brass ones here. So one input port and one output port. It's got a screw in the top. See that slotted screw? You can turn that. That's what adjusts the amount of restriction. But it'll only restrict one way. If we connect this side to main air, what was it, guys? If we connect this side to main air, then whatever's coming out here will be flow restricted, because this one restricts going in that direction. How do I know that? I know that because it's printed on the body of it. Now obviously, again, you guys ain't going to be able to see that. You might be able to see that there's stuff on there, but you won't be able to make out what it was. You might be able to make out a wee arrowhead there and a wee arrowhead there. You can see that one's pointing, they're both pointing in, but there's text above and below the arrow that I don't think you can see. Let me check, see if I can get another camera. Hold on. There you go. Right, so that's, you can see it's printed full flow goes this way, adjusted ADJ, adjusted or restricted flow goes that way. So, yeah, that's your unidirectional flow restrictor. So that's the actual symbol, oh sorry, that's the actual component for unidirectional flow restrictor. Well, we're on here. I know you couldn't see it earlier, but there's the body of the 5.2 valve, and you can see the symbol printed on the body of the 5.2 valve there. So you should always be checking for that to make sure you don't mix it up with a 3-2 valve. Right, so let's change this camera back over to my smiling face. Here I am. And move that bad boy out the road. Right, so that's what a unidirectional flow restrictor is. How do we use it? What do we use it for? We use it for speed control. Let's move me over here. Okay, cylinder speed control. So we'll have, I'm going to stick with a double acting cylinder. If we want to control the speed of outstroke, we're going to control the air coming out of the cylinder, right? So for speed control, we always control the exhaust air from the cylinder. Now, I can't remember what I said. So let's say we want to control the speed of outstroke. That would mean that when we're controlling the speed of outstroke, we are increasing the air on this side. This is the outstroke port. Okay. So if we're controlling the speed of the outstroke port, air is going to be coming out of the other one. Exhaust air is going to be coming out here. Exhaust during an outstroke. Alright. So when we're outstroking the cylinder, we're putting air in here, and any air that's inside here gets pushed out of the cylinder on that side. And it's the exhaust air that we want to restrict. So that means that we're going to put a restrictor on this side. So a restrictor is going to go in here. Now remember, we use unidirectional flow restrictors, and the reason we use unidirectional flow restrictors will be apparent in a wee second. So we're going to put a unit. What way should it be facing? Right. So we want to restrict the exhaust air. So if the exhaust air is going that way, that's the way that we want to restrict. So that's where the unidirectional flow restrictor would be drawn to control the speed of outstroke. To control the speed of outstroke. Now then, hopefully it's kind of obvious where you would draw the unidirectional flow restrictor to control the speed of instroke. Because when it's instroking, we'd be putting air in here and exhaust air would be coming out that side. So obviously, to control the speed of instroke, we'd put the unidirectional flow restrictor over here. Make sure it be facing the same way. It should always be facing the same way as the exhaust air. So it's always pointing away from. Different colour. Let's go for orange this time. Yeah. So a restriction is always pointing away from the cylinder. So we always control the exhaust air. So that's a fancy way of saying it's always in the wrong one. If we're controlling outstroke, the UDR should be over here. And if we're controlling instroke, the UDR should be over there. And the restriction always points away. Okay, and again, all I'm going to do now is set up a couple of questions asking you to draw the unidirectional flow restrictor in the correct location, and then I'll maybe put up another circuit, a bigger circuit, where I ask you to do a parts list, explain and describe the operation of the circuit, and maybe spot an error. But I think you probably know what the error is going to be now, right? Okay, so let me put these questions up and leave that for you. Right, so these are the questions. Draw a cylinder combined with a unidirectional flow restrictor which controls the speed of instroke. And then for this circuit here, I want you to create a parts list and explain the operation. You probably want to draw it and explain the operation of the circuit and do a parts list for it. That's just based on what I did on the previous slide. And then in this one, explain the operation. Now remember, when I was asking to explain this, I want you to draw in as much of the previous stuff as you can. So there's logic control used in the circuit that you should talk about specifically. And there's speed control. So there are 4 deliberate mistakes to find too. 3 of the deliberate mistakes, they're just symbol errors. Alright, one of them's a functional error, so you have to find it and fix it. So when you draw it, you should draw it hopefully correctly. Now, I realise that I'm talking about speed control, and just in case it's not clear, okay, in here I've talked about what a flow restrictor was, and if you adjust it you can reduce the flow. So the idea, let's not talk about that one, let's talk about the example one from the previous page here. So with this guy, if we provide air in here, the exhaust air that's coming out is all going to have to go through that restrictor. So if we tighten the screw up on the restrictor, remember the screw on the actual flow restrictor itself, if we tighten that screw up, we'll increase the value of restriction, which means the air that's going to try to get pushed out of here is going to be pressurised against what's coming in. So basically what's coming in can't just move it over nice and quickly, it will move it over slowly as it squashes the air out. Right? This rule about exhaust air, the fact that you would think that you could just put the restrictor on that line facing into the cylinder. If you put it on that side facing into the cylinder, it will still move slowly, but you might get jerky motion. Yeah. Restricting the exhaust air keeps the movement smooth but slow. So that's what this is all about. So there's your 3 questions to do, other than maybe taking down notes of this stuff that I've done. You probably want to record this stuff in your jotter. But this is the 3 tasks here. This is like the stuff on the worksheet. Okay, all the best.